Sample exam 7, question number 1. In a particular softball league, each team consists of 5 women and 5 men. In determining batting order for the 10 players, a woman must bat first and successive batters must be of opposite sex. How many different batting orders are possible for a team? Answer to question number 1 is if the first batter must be a girl, there's 5 choices. And then the next choice has to be a boy, and there's 5 choices. After that, it has to be a girl, and there's 4 choices remaining after the first one's picked. And then there's 4 boys, and then 3, 2, 1, 1. And so that's 5 factorial times 5 factorial, which is 5 factorial squared. Question number 2. Suppose 30% of all electrical fuses manufactured by a certain company fail to meet municipal building standards. What is the probability that in a random sample of 10 fuses, exactly 3 will fail to meet the municipal building standards? Number 2, this is a classic binomial. So if n is 10, p is 0.3, x the number of fuses that fail, we want to find the probability that x is exactly 3, and then that's the formula. Problem number 3. An urn contains 3 red balls, 2 green balls, and 1 yellow ball. 3 balls are selected at random and without replacement from the urn. What is the probability at least one color is not drawn? In this case, we want to find the probability that at least one color is not chosen. This is your classic hypergeometric, and there's 3 sets of combinatorics here. The first one represents the number of red, number of green balls, number of yellow balls. So let's first find out the number of ways that we can have no red, and that's with 3 choose 0. And then we have to choose 2 of the green and 1 of the yellow, and that's the total number of ways we can have no red. Now no green means that we're choosing 0 from the green. So we could have 2 red and 1 yellow, or 3 red and 0 yellow. It's just the number of ways to have no green. Now this one also has no yellow, but we don't want to count it twice. So, and then these are the other 2 ways that we can have no yellow. We have 1 red, 2 green, or 2 red and 1 green. So when we calculate, and then this is divided by the total number of ways we can choose 3 balls. And then this is 1, this one is 3, 1, 3, 6 over 20. The answer is 7/10. Question number 4. Let the continuous random variable x have the density function f of x as shown in the figure below. What is the 25th percentile of the distribution of x? Now number 4, we want to find the 25th percentile. So that if this is our distribution, we want to find p such that this area is 0.25. Okay. But first of all, we have to choose this value. And so this area has to be 1. And it provides in the answer that the height is 1/4, and this is A. So the probability of being less than or equal to A has to be 1. And so it's 1/2 the height times the base, and then you can back solve for A and you get A equals 8. Now you can, this ends up being the function, so you can integrate that if you want, but I think it's easiest since this is also a triangle. Oh, actually I use that for this triangle. So this is the function for the height. When we're at 8, we're at 1/4. When we're at 0, we're at 0. So we want this area of the triangle to be 0.25, so the probability of x being less than or equal to p is 1/2 the height times the base, you can solve that. You get p squared is equal to 16, or p is equal to 4. Number 5. Let x and y be random variables with variances 2 and 3 respectively and covariance -1. Which of the following random variables has the smallest variance? Now number 5 is it's sort of just a crank and grind method, a lot of trial and error. So here's the generic formula for variance. The variance of this linear combination, ax plus by, is you take the a out and you get a squared, and it's the variance of x. And then it's plus, you take the b out and you can square it, you get b squared plus y. But then you have 2 times a plus b times the covariance of x and y. Now, I'm not proving it here, but it's straightforward to show, and this is something you should just commit to memory anyway. So then for each of these equations, you plug into this equation and you get a number. And so the first one, we get, 4, variance of x is 2, it's a implied 1 there, so 1 squared is 1, variance of 3, 2 times 1 times the covariance is 7. And if you do that for each of the rest, then you'll get these numbers, and you'll see that question A is the smallest. Number 6. Let x1 through x4 be a random sample from a normal distribution with unknown mean and known variance equal to 9. Let s squared equal this quantity. What is the probability that s squared is less than k is equal to 0.05? Then k equals. Now, number 6, we want to find the probability that s squared is less than or equal to k is equal to 0.05. And we want to find k. So here, we have a sample of 4, and to find, so we want to make this a chi-squared. So if you take the sum of the squares and then divide it by its variance, then that ends up being chi-squared. So in the neat thing about improbability, if we do the same thing to both sides, it doesn't change the probability. So here we multiply both sides times 3/9. Now, this is to illustrate that this sample variance is divided by n-1, divided by 3. So we get rid of that 3 in this denominator, and then we divide by the variance, which in the problem they said is 9. So really we could just divide by 3 to both sides, but I wanted to illustrate that point here. So here's a note that this quantity squared divided by the variance is chi-squared with n-1 degrees of freedom. So here we have this quantity, which reduces to this, which is chi-squared 3. And a chi-squared 3, 0.05 is 0.35. So if this is chi-squared, then this quantity is 0.35. So you set this quantity to 0.35, solve for k, and you get 1.05. Number 7. Let x and y have a bivariate normal distribution. Which of the following statements must be true? Number 7. Here, a non-zero linear combination of x and y, assuming x and y is bivariate, always has a normal distribution. Some people use that as the definition of a bivariate normal distribution. So this is always true. So then it asks us what this expectation is. they said it was a linear combination of the x's, and this is these actuarial exams use this formula so much. It's something you should commit to memory, and this is a linear function in x, so number 2 is true. And number 3, the variance of this conditional is this, and this is, these two go hand in hand. You just almost have to memorize those for the test. We could go through and prove it, but I think you won't have enough time on the test to do that. You should just memorize it. So if this is the variance of that, and that's the variance of the unconditional, then since this number is always 1 or less, then this number is always less than that. So it is true. So the answer is I have D. Oh yeah, 1, 2, and 3 are all true. Number 8. Let x1 through x4 be a random sample from a normal distribution with unknown mean mu and unknown variance sigma squared. The null hypothesis that mu is 10 is to be tested against the alternative hypothesis mu is not equal to 10 at a significance level of 0.05. Using the student's t-statistic, if the resulting sample mean is 15.84 and the sample variance is 16, then what are the critical t-value and the decision reached? Number 8, we want to do a hypothesis test, and it's stated that we're doing a student's t, which is x minus the null hypothesis divided by the sample standard deviation divided by the square root of n. So if we just plug in the numbers, we get 2.92. And then when we look this up in a t-table, and it is a two-sided test, so this area is 0.025 and this is 0.025, 3 degrees of freedom, we get 3.19. So this value is in the do not reject region. It means we don't have enough evidence to reject the null hypothesis. Okay. Number 9. The number of automobiles crossing a certain intersection during any time interval of length t minutes between 3 p.m. and 4 p.m. has a Poisson distribution with mean t. Let W be a time elapsed after 3 p.m. before the first automobile crosses the intersection. What is the probability that W is less than 2 minutes? So problem number 9, we want to find the probability that our wait time is less than 2 minutes. This is an interesting, I'm going to solve it 2 different ways. So this is the first approach, is we're going to use a Poisson distribution. But let me go to this side note first. A Poisson variable, say n, is distributed with Poisson lambda t. Now lambda is the rate of events per standard unit, and then t is the number, it's times the number of standard units. So if we want 2 standard units, that's 2 or 3 or 1.5, then this is the new parameter for the Poisson. And so the problem here, they say the expected value of the expected number of events is t. So they say, and our problem deals with 2 minutes. So the expected number of events within 2 minutes is 2. And so if we think of this as our parameter and we back solve for lambda, lambda is 1. So that tells us that we expect 1 event per minute. And if we look at it for 2 minutes, then we expect to see 2 events. Okay, and I'll elaborate a little more on this in the second problem, or the second solution. So here n is a Poisson with 2. We expect 2 events within the 2 minutes. And so the question is, what's the probability that the wait time is less than 2? Meaning we see 1 or more events within that 2-minute window. So you can solve that by 1 minus the probability that we see no events, and then plugging 0 into our variable into a Poisson density. It simplifies to this. Okay, and so now I want to look at the second solution, and there we're going to deal more with the waiting time as opposed to the Poisson. So here, if n is a Poisson with this rate, and w is the waiting time for the next automobile, or the waiting time within that interval, t. I think of it like this. So we're looking at an interval from 0 to t, and the probability that we see 0 events in here is the same as the wait time for an event is more than t. If the wait time is more than t, we saw 0 events. So these two are sort of equivalent states. So here, the probability that the wait time is greater than t, that's equal to the probability of observing 0 events within that time interval. And if this is a Poisson, so we plug in 0 to our variable into the density, that simplifies to this. Now let's look at 1 minus that. So this is the probability that w is less than or equal to t is equal to so if the wait time is less than t, meaning we see at least 1 automobile in here, that means we observed 1 or more events. And so that's 1 minus what we got here, which is this. Then since this is a CDF, if we want to find the density of w, so we want to find the f of t, so the density at t, we take the derivative of this CDF. Well, this was here, so we put it in here. So take the derivative of this, we get lambda e to the lambda t, which this is exponential. So that's how Poisson and exponential are related. So that's kind of a neat little thing to see there. So now the probability that the wait time is less than or equal to 2, so we plug in 2 here because that said that our mean wait time, our mean number of events is 2, so this is 2, and we get the same answers before. Okay, that's all I have for this video. Hope you enjoyed it. Please like it if you did, and subscribe so you don't miss the next one. Thanks. Bye.